So let me, can I take this? Because otherwise I don't see. So just a little bit of history for people that do not know too much about brain cell transplant. And this is just to remember that if you think to be the first, you have to change your idea, because the first transplant of brain cells was performed in 1819 by Gilman Thompson, who was publishing a paper in the New York Medical Journal. So we are in New York, and we can celebrate it. And he was demonstrating that he could transplant brain cells from a cat hemisphere to a dog hemisphere, and the cells were not rejected. Of course, he didn't know anything about that, but of course he was surprised by that, and actually this opened a new avenue of brain cell transplant, but also was the foundation of neuroimmunology, actually, because of course from that on, scientists tried to understand why the cells were not rejected once transplanted into the brain. But this is another story. So regarding the brain transplant, then in the coming years, people demonstrated that brain cells could be transplanted and they could survive. They could not only survive, but they could also be integrated functionally into the brain upon transplantation. And at the end of this period, in 1987, the group from Lund, Anders Björklund in particular, they demonstrated that if you transplant brain cells into the striatal area in rats with Parkinson's disease, they could start producing dopamine, and they could try to relieve from Parkinson's symptoms. And actually in 1991, the first patient with Parkinson's disease was transplanted with fetal ventral mesencephalon cells, which were considered to be the progenitor of dopaminergic cells. So from 1980 to 1919, actually, we knew already that there were neural stem cells in the brain, of course, but until that time, we were not able to obtain those cells and cultivate them in vitro to expand them. But thanks to these colleagues, techniques were developed, and from 1990 on, we could use a very simple system in the lab to make neural stem cells proliferating, whatever was the source of such cells. So at that time, we had a sort of unlimited source of cells, of neural stem cells, which is not possible before, because when ventral mesencephalon fetal cells were transplanted, they need to have 7 fresh fetuses at the same time for transplanting one single patient. And that's obviously quite complicated if you think of using this technique in therapy in routine settings. So nowadays we have a lot of neural stem cells. We have stem cells from everywhere. We can get pluripotent stem cells from ES or iPSCs. We can get stem cells from embryonic tissue, fetal tissue, cord blood, adult cells from mostly everywhere. And of course, you can put these cells in culture and to derive all different types of cells, including neural stem cells, which is the topic I'm going to focus today. So at that time, which was the principle of brain cell transplant? So the principle was very simple. We transplant neural stem cells or progenitor into areas in which there are damaged cells, and the idea was that those cells could replace physically damaged cells in order to regain functions. And this was something which was performed also, of course, in humans, not only in Parkinson's disease, but also in Huntington disease, ALS, Batten disease, Pelizaeus-Merzbacher, spinal cord injury, stroke. So there were many, many attempts in different types of patients of trying to transplant those cells. We are still waiting for the result at the end, but at least some of them at least concluded the phase 1 positively. Nowadays, there are 4,000 trials of stem cells in the world, which is a lot. But as you see, as you look at this slide, only 22 are dealing with neural stem cells. And this should make you aware of the fact that it's quite complicated to deal with those cells in terms of making them proliferating in vitro. They have a long time of replication, 28 days for human cells, so it's really complicated to cultivate these cells in vitro in the lab. Anyhow, in 90s, at the end of 90s, we decided to try to face this disease that you know quite well. And of course, we understand immediately that it was impossible to think of transplanting neural stem cells in each single lesion every time. It was intraparenchymal. Of course, was not possible, routinely speaking. So we thought that we could try to use blood on one end and CSF on the other end to try to deliver the cells into the damaged area. And this is the summary of the work which has been done in the past 20 years. I should acknowledge also Tamir, which is here, Tamir Benur, and also Jamie Mitola. They were two labs along with my lab working on this, and so I'm grateful for the work they did. And at the end of the story, we can summarize the situation in this way, because we have whatever is the source of stem cell, they can be injected in the blood, in the CSF, in the parenchyma directly, and they show to have a sort of pathotropism. They can get exactly where the lesions are, and this is because they are expressing on their surface. Of course, we have been characterizing the molecular mechanism of all these steps, because they behave such as immune cells. So they tater, they rolling, and they extravasate into the tissue, of course, when they find some inflammatory area or damaged area, through chemokine receptor and adhesion molecules. So the point is that when they get into the tissue, what is interesting is they start a dialogue with the tissue. They try to understand which is the microenvironment they have to confront with, and once with the microenvironment, they can decide to do many things. Of course, they can cell replace, as it has been shown in Parkinson, but they can also promote trophic support by releasing trophic factors. They can immunomodulate, and they can also support neural plasticity. So this is the beauty of the cell therapy, because this cannot be obtained using whatever drugs we can think about. And so until 2000, we thought that we could use stem cells to replace cells which were damaged. But from 2000 on, we proposed this bystander paracrine effect, which is the way of stem cell remaining undifferentiated to produce and secrete molecules with neuroprotective features. And actually, from those studies, I mean, the concept of secretome, of course, came out. As you know, there are many people thinking secretome could be used instead of stem cell now, but actually, this was the founding data from supporting this way of thinking. So we started in 23, working in mice, in experimental autoimmune encephalomyelitis. We then moved into monkeys in 2009, and we started the phase 1 trials in 2017 in humans. So the first challenge we had to face was the way of producing cells, because again, even if you are in academic setting, you have to produce cells as in a cell factory, as in an industry. So the first problem was to develop this kind of strategy, and this is what we did. It took quite a lot of years, but at the end we were able to get billions and billions of neural stem cells from one single fetus, and this was important because from one single fetus we calculated we could get up to 200 billion of neural stem cells. Then we had enough cells to set up a trial, a phase 1 trial, a dose-escalating trials in which we started injecting different doses of cells, increasing doses of cells intrathecally, which was the way we decided to use. We selected one cell line, and this cell line was quite interesting because we decided to select a line in which there were some markers expressed on their surface, which were the marker that we think are making the cells migrating within the CNS. You see CD133, CD29, CD44, 6ER4. Jamie worked a lot on 6ER4 for the migration property of those cells, and Nestin and SOX2, which are two markers of neural stem cells. The fetus was a fetus of 10, 12 weeks post-conception. Then we had to, of course, generate a drug product, which was, again, another quite nightmare because we had to produce all these different items. We have to check everything in order to have a safe product. And then when we got the drug product, we decided to set up the trial. And we enrolled 12 patients with with progressive multiple sclerosis. They took immunosuppression, of course, because the transplant was an allogenic transplant. prednisone for 30 days, and then immunosuppression drugs, tacrolimus, for 2 years. So we've been following the patient after transplantation for 2 years. So the trial was quite simple because we took 12 patients with an EDSS more than 6.5. Those were the patients that the regulatory agency allowed us to transplant. We transplanted 3 patients per dose. We started with 50 million cells intrathecally in 3 patients. We had to wait 15 days between the patient, and then 3 months before moving to the second dose, which was 100 million cells, and then the third dose with the same scheme, 250 million per patient. At the end, we ended up with 3 patients in which we injected 500 million neural stem cells. Then we have been taking back CSF after 3 months, and we have been following the patient with MRI, of course, and neurophysiology and clinics. So, sorry. Those are the patient enrolled. As you see, I mean, they were quite compromised because they had an EDSS, a mini EDSS of 7.25. The system we developed was very simple because we got the bag with the cell in the morning, so we put the cells into a syringe, very simple, and then we injected them with an intrathecal injection. Very, very simple, can be done in the room of the patient. So primary endpoint were safety and tolerability, and actually the transplant was very safe. This is the short and midterm adverse event. As you see, we didn't see any major adverse event. Most of the adverse events we recorded were related to the lumbar puncture. Then we look at the side effect, long-term side effect, and as you see, we didn't record any side effect of grade 3 or 4, apart from one relapse, which was occurring 1.5 years after the transplantation. So, of course, we recorded it, but we didn't associate this relapse to the transplantation because it was too far from the injection. But anyhow, again, even the long-term side effects were quite reassuring. Then, of course, we studied a lot of secondary exploratory hypothesis generating endpoint to understand a little bit more. And first of all, the clinic didn't change, as you see, although there were 10 out of 12 patients which had a progression which was lower than the 2 years before, but don't forget that could be a simple regression to the mean, so this does not mean too much. But to some extent, we didn't see any major worsening, and this was important, even because when you have patients with 7 EDSS, of course, those minimal changes are difficult to record, as you can imagine. Again, neurophysiology, neuropsychology, and evoked potential, everything was done, but we didn't find any difference between the patient and the different doses of cells used. And then we, of course, 3 months after transplantation, looked into the CSF if we could measure, if we could find some neural stem cells. And actually, in 1 patient out of 5 in which we obtained enough cells to run the PCR, we could find 3 months after transplantation still neural stem cells circulating. This was the patient in which we injected the highest number of cells, 500 million, as I told you before. But this was again reassuring because this means that at least there are cells continuing circulating within the CSF where there are released substances. This was the hypothesis, and therefore it was interesting to note that the cells were still remaining. What about the immunological profile? This was again interesting because, as you can see, there was a major change in the CSF after 3 months. And of course, as expected, at least we were expecting, there was an increase in trophic factor, anti-inflammatory cytokines, and therefore there was a sort of shift towards a more anti-inflammatory profile of the CSF 3 months after cell injection. Interestingly enough, when we do CSF untargeted proteomics 3 months for transplantation, we found that there was a lot of enriched pathways which were related to neurons and not to myelin. And this was, again, interesting because there was pathway generation of axons, synapse formation, and protection of neurons. Those were pathways which were highlighted after 3 months, and this was important. And therefore, again, this was quite reassuring, or at least in line with what we were expecting. And then we found an interesting result because we found that more cells we injected, less brain atrophy was accumulated by the patient over time. In particular, less gray matter atrophy. And this could not mean too much because we are talking about 12 patients. We have to be very, very cautious. But interestingly enough, I would take this data as a sort of dose-response curve rather than an indication that they were protecting brain from losing cells. And again, this is in line with what we were expecting and with the proteomic analysis we performed on the CSF. But this is something really important because half of the patients developed new lesions. And among these 6 patients, 3 of them displayed also gadolinium-enhancing lesion. As you see, those lesions were mostly appearing in patients taking the highest amount of cells. Of course, we did all possible, we tried to see all possible correlation with the CSF data and proteomic data. We couldn't find any correlation between these events. And, but interestingly enough, on the other end, there was one patient, number 12, he had a gadolinium-enhancing lesion before transplantation, and the lesion disappears after transplantation. So anyhow, this is something which should be considered with cautious, and that's the reason why we are deciding to run the phase 2 using 250 million cells divided in 2 doses 6 months apart, because we think that when you inject such number of cells, of course there is a lot of debris in the CSF because most of the cells are lost when you inject them just by the mechanical pressure. And therefore, we prefer not to take too many risks in the phase 2 trial. So this is what we obtained so far. And what we can say is that those data are reassuring. So they are, of course, pushing us to run a phase 2. And therefore, we think it's worthwhile to try to do it. Let me tell you a little bit what would be the next future of brain cell transplant, because this is what we are here, to discuss about. And certainly, the fact of using allogenic fetal cells means that you have to immunosuppress your patient, and immunosuppressing them means that you have to give antiviral, antibacterial drugs at the same time, and those are patients which are already compromised to some extent, and the cure could become really heavy to support. And therefore, the only way to go is to use induced pluripotent stem cells, which is the way to try to generate cells with autologous cells. And we already tested those cells some years ago in experimental autoimmune encephalomyelitis, and again we found exactly the same as we found with syngenic adult mouse cells. And there was a protection from demyelination, and there was also an axonal protection, at least in the animal model. However, the point is the following. Are the cells that we generate from multiple sclerosis patients safe? Or do they harbor some alteration that could be a sort of obstacle to use those cells in clinics? So thanks to the work of Tanya, who is here, and Anik van Everkoren, through also thanks to the PMSA, of course, because this was one of the triggering events to make us working together and generating new data. Apart from the PMSA work we were doing, of course, there was a lot of byproduct that we were happy to generate. We were able to generate neural stem cells, oligos, astros, and neuron from both primary progressive and relapsing remitting MS, and then Tanya did a great job because she demonstrated, for example, that if we take oligodendrocyte derived from neural stem cell from people with MS or controls, but also from monozygotic twins discordant from MS, she couldn't find any difference in terms of protein expression between the two cell types, indicating that those cells were quite similar to each other. And again, when in vitro, she tried to set up the nanofiber system to prove their remyelination potential. Again, she found the same between oligos from patient and oligos from controls. And again, Anik van Everkoren did an in vivo work. she has been generating this very, very interesting model. Is a shiver rag minus mouse in which human iPS-derived oligodendrocytes were transplanted when those mice were pup, and therefore at the end we had mice with human myelin, which was interesting, and again human myelin was able to remyelinate axons and to generate fresh and functional myelin, as you see from neurophysiology, even in this setting. So at least so far, we have been studying few, I must admit, clones, which is not an easy task, but it seems that those cells are quite similar, and maybe those neural stem cells from a patient can be easily used instead of fetal neural stem cells. So this is more or less the final slide. I mean, and of course, we have been demonstrated that transplanted stem cells do not work therapeutically exclusively to cell replacement, but also via bystander effect. It's like a Trojan horse, taking into the brain a lot of substances, in particular trophic factors, as I told you before. MPC from adult or embryonic tissue exert neuroprotective effect by secreting trophic factor and immunomodulatory molecules, and it seems, frankly speaking, it seems that all different types of stem cells are doing the same. They are not working physically, substituting cells, but they can work also by releasing substances. I'm talking about hematopoietic as well as mesenchymal stem cells. So bed-to-bedside translation is just started, but there are a lot of pending questions we have to solve. But discovering the mechanism of action of neural stem cells could be an advantage to try to foster this kind of study in the future. So what we think is the situation now is the following. When we have inflammation, neural stem cells injected into an inflammatory environment, they don't proliferate. Again, we demonstrated this is because interferon gamma and TNF-alpha do block cycling kinases, and this is the way why pro-inflammatory cytokines do not allow those cells to proliferate. While being undifferentiated, they start to release what they do release because they are stem cells. So of course they are releasing secreting factors which are good for the body. And this is the reason why they can immunomodulate and promote trophic support. And this is in a sort of non-cell autonomous fashion. While if we have cellular degeneration, like in Parkinson's disease, of course you have to transplant neural stem cells which are already pre-committed in vitro to becoming, in this case, dopaminergic cells. When you have pre-committed these cells in vitro, they do behave in a sort of cell autonomous fashion, and then once they are injected, they can differentiate into neurons, for example, oligodendrocyte and astrocyte. Therefore, the scenario now, 20 years after the starting of those kind of studies, is completely different from what we thought before, and therefore it's another opportunity to try to make this attempt a real therapy.